Hey everyone, and welcome to this explainer. Today, we're diving into literally the ultimate billion-dollar dilemma in offshore engineering. I mean, imagine you've got two massive underground oil reserves and they hold the exact same volume of oil. But one of them practically begs for a platform with the wells right on top, while the other demands a floating vessel with wells scattered all across the seabed. If you choose the right concept, boom, you've got a highly efficient, profitable asset. But if you choose wrong, well, you've just committed several billion dollars to the absolute wrong machine and completely tanked the project's economics. So today, we are mastering concept selection.
All right, let's jump right into this. We're dealing with two fundamental reservoir shapes here. First up, we have what engineers affectionately call a potato reservoir, and yeah, just like it sounds, it's this compact, thick body of oil clustered tightly together deep underground. On the flip side, we have a pancake reservoir. This is a wide, super thin body of oil that just spreads out across kilometers and kilometers of the seabed. Now, remember, both of these reservoirs hold the exact same volume of hydrocarbons, but they demand completely opposite engineering concepts to actually get that oil up to the surface. So here is the incredibly high-stakes question. Which concept do you actually build? You see, in offshore development, you can't just slap a standard rig on top of any random oil field. You really have to know the rules of the game here. If you misjudge the physical realities of the reservoir, you don't just, lose a little efficiency. No, you end up building a machine that physically cannot drain the field. Or one that costs so astronomically much to operate that you completely destroy your profit margins. It's honestly fascinating how the physical shape completely dictates the hardware. So a potato-shaped reservoir is compact, right? Because it's tight, you can reach most of that oil from one single surface location. And this heavily favors what we call a dry tree. That basically means the wellheads are brought all the way up onto the platform deck, high and dry above the ocean, where operators can literally just walk up and touch them. This points you directly to a TLP, a tension leg platform, or a SPAR platform. These give you direct well access, way cheaper interventions, and just overall better management over the life of the field. But then, look at the pancake reservoir. It's thin, and it sprawls over a massive area. There is absolutely no single surface point that can reach it all. So the wells have to go down on the seabed, and we call these wet trees. These scattered subsea wells are then tied back to an FPSO, which is a floating production storage and offloading vessel. Basically, you're trading direct, easy access for incredible reach. Think of it kind of like an orchard versus a wheat field. If you're harvesting a dense apple orchard, you can stand in one central spot, set up a tall ladder, and just pick almost everything around you, right? Well, that's your compact potato reservoir with a dry tree platform. But if you're harvesting a vast, thin wheat field, a ladder's completely useless. You have to send these roaming machines across the entire field, which then feed all the wheat back into one central collection truck. That is your pancake reservoir, with subsea wet trees feeding back to an FPSO vessel. I mean, nobody harvests a wheat field from a ladder, and nobody sends a fleet of huge combine harvesters into a dense little orchard. Section 1. The hard limits of depth. This is exactly where physics steps in and essentially closes options for you. See, as you go deeper into the ocean, physics starts vetoing your choices pretty fast. A tension leg platform, or TLP, relies on these massive steel tethers pulling the floating hull down to the seabed. But those tethers, they max out around 6,000 feet of water depth. Beyond that, the whole tension leg system just stops being structurally viable. And what about a SPAR? Well, a SPAR is this massive cylindrical hull, but it has to physically carry the full hanging weight of its steel risers, stretching all the way down to the ocean floor. Because of that immense weight, SPARs hit their structural limit at roughly 5,000 feet. However, subsea wet trees? They have absolutely no depth limit. None. So once you cross those 5,000 and 6,000 foot thresholds, well, the choice pretty much just makes itself. Okay, here is a scenario that literally catches people out all the time. Imagine you have a beautiful, perfectly compact, potato-shaped reservoir, but it is located in ultra-deep water at 7,500 feet. Think about the rules we just covered. Which concept do you choose here? Take a quick second and lock in your answer. So, the absolutely crucial point here is this. Depth completely overrules shape. Every time. Yes, the compact potato shape desperately wants a dry tree platform like a TLP or a SPAR, but that 7,500-foot water depth immediately vetoes both of them. The tethers won't work, and the risers are just way too heavy. So your resulting concept automatically defaults to a wet tree, subsea, FPSO system. Because of the sheer depth, you are forced to accept the much higher intervention costs of needing a highly specialized vessel every single time you want to do maintenance on a well for the entire life of the field. This entire process we just walked through, it's called concept selection. It is without a doubt the absolute most critical phase of a project. It's where unchangeable physical factors dictate your viable engineering choices before a single dollar of feed, that's front-end engineering design, is even spent. You came into this explainer probably able to deliver a concept someone else chose, but you leave empowered to actually challenge that choice. Before anyone starts cutting steel, you now know to ask, hey, what shape is the reservoir? What is the exact water depth? Is the concept sitting on the table actually physically viable?
I want to leave you with this defining thought from our source material. Depth overrules shape. Physics has the final vote, and it doesn't negotiate with a business case. I mean, you can build the most beautiful, optimistic, economic model in the boardroom, but if the tethers won't reach or the risers are just too heavy, the ocean simply does not care. But here is a provocative question to take with you. Just because a concept is physically viable, does that actually mean it will be economically profitable? Especially when the global price of oil suddenly drops. That structural gap between viable and profitable is a completely different battlefield, and one we are definitely going to explore next time. Thanks so much for joining me on this explainer, and I'll catch you in the next one.